So start another record. Okay, so let's go over the absolute loss and the generalization as the last part of our lecture. Okay, so can maybe Chloe, can you help us read this paragraph?
Similar to the squared loss, the absolute loss function is also typically used in regression settings. It suffers the penalties hxi minus yi because the suffered loss grows linearly with the mispredictions. It is more suitable for noisy data when some mispredictions are unavoidable and shouldn't dominate the loss. If given an input x, the label y is probabilistic according to some distribution p(y(x), then the optimal prediction to minimize the absolute loss is to predict the median value. For example, hx equals median p(y(x). Formally, the absolute loss can be stated as,
Yeah,
yeah.
just ignore this. Yeah, okay, cool. So there's a one thing that's really important. It's more suitable for noisy data, right? This. And I don't know if someone understand this, right? So you remember, like in the square laws, we say if we encourage no prediction to be really far off, right? So if a prediction is really far off, since we have a square, right? So if you are missing, so if hx and y is 5 apart, then we are adding 25. If they are only 1 apart, we are adding 1, right? So 1 and 25 are like a very large difference, right? It's not like 1 and 5. 1 and 5 is difference just 4, but 1 and 25, the difference is 24, right? So if you are making a square loss, you are penalized for being really far off. But here, in noisy data, we said some mispredictions are unavoidable. Okay, so let's divide the sentence into two parts. So it means like noisy data are in something. Noisy data means like in some scenario, our some mispredictions are unavoidable. So can each of you give some real world examples when mispredictions are unavoidable, like when you train data and you expect some misprediction to happen? Okay, let's first think about it for 1 minute, and I want most of you to give an example when you think. It has no, it's an open-ended question. It has no correct answer, no single correct answers. Lots of answers are correct, and I want each of you to give some examples, like when making what predictions, mispredictions are unavoidable and should not be penalized, right? Because in the square laws, mispredictions are penalized in a very severe way, right? If you mispredict a lot, then we are penalizing a lot. But in absolute loss function, we are not penalizing you so much, right? So if you are 5 and 1, we only penalize you for 4, right? Increase the loss function by 4. So by penalize, we mean increase the loss function, right? We only increase the loss function by 4. Yeah. So maybe Mark, can you give an example that you think mispredictions are unavoidable? Any example? Yeah. Like in real life, in your experience, you think mispredictions are unavoidable. It can be anything. Yeah. Or maybe Andrew, can you give an example or any guess? Yeah.
Um,
It can due to
hmm,
anything. It can due to anything. You don't need to think it's a perfect world. And I mean, perfect world, there shouldn't be no misprediction, right? You may have a lot of constraints.
yeah,
Yeah.
like examples of like a misprediction or like just the data.
It can be anything. Misprediction because of data. It can be even this way. Yeah.
Hmm, maybe like weather. I don't know.
Yeah. So let me give you an example. Like when like in the example for image like recognition, right? You are recognizing human faces. Misprediction are of course unavoidable because two humans can be very similar in terms of faces, right? They are twins, right? So misprediction between twins are unavoidable. That's of course, and it can also due to like objective constraint. Why? Say I've collected 100 images, right? But the images when so I take pictures, right? So I take pictures and upload the pictures. But the pictures I took, I'm using a very old camera, right? That old cameras are taking really vague pictures. So if our computer trains on vague pictures, it is really easy to make a lot of mistakes, right? So in this case, mispredictions are of course unavoidable because the image is vague. So it's a sort of like garbage in, garbage out, right? So because of the vague image, so vague image by vague image we really mean that the number of pixels are small, right? And so remember in the last lecture we said pixels are feature dimensions, right? If the image has 100 pixels, it will be a 300 dimension because each pixel correspond to three dimension. It's the red color, green color, and blue color, right? Each pixel is RGB in three dimension, and 100 pixels is 300 dimensions. And if you are predicting with 3000 dimension, of course you will get better results than predicting only with 300 dimensions, right? Yeah. So that's it. So that's the case when misprediction are unavoidable. So it can either due to your input data, right? Your input data is imperfect, it's like vague. You are using an old camera or like you are recording GPS of cars and your like a recording machine just like broke or does not. And I mean, of course, you're recording. It's like sensors, right? You are using sensors to get the GPS, get the velocity of vehicles, and the sensor can stop working, right? And if the sensor stop working from time to time, of course you can make mispredictions because your data is inconsistent, your data is like missing. Yeah, and also even if your data is perfect, your data may be like too hard to distinguish. Just like I said, you may encounter twins in face or image recognition. Yeah, and if you are like making predictions between weathers, right? And weathers like for example, so weather is like of course mispredictions can happen, right? Because no one can like weather like a lot of forces are influencing weather, right? So for example, we are using five features to predict whether tomorrow will rain or not. But maybe there are other features also influencing the whether it's rain or not tomorrow, right? So we are using only five features. Maybe there are hidden features out there, right? There are features that we omit, that we neglect, which also will influence the model or influence the result, the answers, the output, right? It will also influence the output or the labels of the true labels, right? Whether it's rain or not. Yeah, so we are just input of five feature dimension data, but in reality, 100 dimension features are out there to influence whether it rains or not tomorrow, right? So say we only takes into account of the season, the years, and also maybe like the gravity, right? The specific gravity and and also maybe like the wind, right? The wind today, like the magnitude of wind, and also the cloud, right? The cloud density. But maybe out there is still humidity, right? There's also like the distance between the moon, right? The moon may also influence whether it rain or not tomorrow because the moon also applies a gravity on the Earth, right? And that gravity takes into account, and also the sun, right? The sunshine and the angle of the sunshine can also influence the rain, right? Maybe it is a specific position between the sun and the Earth and the moon, and it just create a force out there, a mystic force out there, and it influences tomorrow rains or not, right? So we may have too few feature dimensions, and then we omit some crucial important features. So in that case, mispredictions are also unavoidable. So actually, in most cases, the mispredictions are unavoidable, right? Because but it's so whether to use absolute loss or to use square loss, it really depends on how you want to build a model. Do you really want to penalize if you are really far off? Or you say, okay, far off is okay, right? The far off should be penalized, but not that big, right? I mean, for 1-0 loss, you are entirely ignore the far off cases, right? In absolute loss, 5 and 1 are penalized by 5 - 1 absolute value is 4, right? So it's penalized by 4. And in square loss, it's 5 - 1 and squared is penalized by 16, right? 4 squared is 16. And in 1-0 loss, 4 and 1 and 3 and 1 are not that different because 4 does not equal to 1 and it incurs a loss, it's 1. And 3 and 1 are also like not equal, right? They are also different, so it also incurs a loss, and it's 1. So in the viewpoint, in the perspective of 0-1 loss, if you make a mistake, it is a mistake. There's no big mistake or small mistake. So like a 4 and 1 not equal is 1. 3 and 1 not equal is still 1. You are treating them like equally. But in square laws, you are like penalizing for far off data. You think, oh, if it's only 2 and 1, you are not penalizing them that much because 2 - 1 is 1, and 1 squared is only 1, right? So it's quite lenient on those small mistakes, but quite strict on those large mistakes because you square them, right? And in terms of absolute loss, you are saying that okay, it's okay, right? I still want to penalize like when you make a really far off loss, but not that much, right? I won't square it, but let's still recognize how far you are, right? So absolute value measures distance, right? Remember, like 3 and 5, right? 3 - 5 is -2, but if you want to measure distance, you apply an absolute um, operator there, so that -2 becomes 2. Yeah. So that's all we need to know on this, and it's more suitable for noisy data, right? So because if the data, so what do we mean by noisy data? By noisy data, we mean that our data collection method or our data collection mechanism is flawed or is not perfect, right? Because of our old machines, we are collecting some noise, like a vague picture. Vague picture is of course the noise, right? Because the picture does not contain exactly what we want. It contains some like vague pixels out there. Yeah. So for this noisy data, we especially prefer to use absolute loss. Yeah. You see, through these lectures, all of you have learned how to choose among different laws, right? You have learned the square laws, 0-1 laws, and absolute laws, and even you can give a presentation in front of your classmates, and you can start recommending stuff to them, right? Comparing the trade-off between absolute laws and 0-1 laws, and also the square laws. So this is very important. So whenever you learn new concepts and learn multiple types of a new concept, right? Try to learn the trade-off. Try to compare the advantage, compare the difference and similarity, right? In this way, you can give recommendations. You can analyze trade-off. So analyze trade-off really makes you sound like an expert, right? Because whenever an expert, no matter it's a financial expert or like a economic expert or like just an engineer expert, when he shows up in the news or media, he always analyze all comparing stuff and analyzing trade-off, right? So analyzing trade-off really makes you sound smart in front of your classmates, in front of your teachers, and that's a good thing. Yeah. Okay. So at the end of the lecture, let's talk a bit about generalization. So generalization, so it means that so we have so given a loss function, right? So a loss function, so a loss function really depends on the age, right? So once you have an age, you see like so in this example, we don't even give you the specific age. We just give you the result, right? So once the age applied on x, we give you the result, right? So for sometimes I give you x and I give you a specific age. You need to calculate how x plug into that specific age and get the result. And in this example, since my focus is loss, so I make your life easier. I just give the hx results to you, but in most cases you need to calculate hx because you have x and you have h. Yeah. So in general cases, we have a loss function and we attempt to find an h that minimizes the loss, right? So what does this mean? This means that you are selecting Arg is argument. So by argument, it's meaning a changing variable. It means something that's constantly changing, and you want to choose from it. So that means arg. So argmin is like a concatenation of two words. By concatenation, I mean put together. So argmin is like a put together two words. It's argument and mean. So it's finding the argument. Argument refers to this age. So it's trying to find a variable age, or you can say it's a changing stuff, right? So it's trying to finding an age that minimize the loss, right? Because the loss depends on age. Remember, once you have age, you apply it on x, and you get a bunch of hx. With hx and y, you can get the loss function, right? We have practiced it. We have practiced it already again and again, and will no longer repeat that, right? So once you have an age, you are able to get an LH, right? You are able to get an LH, and so what does arg mean here? Arg means here. So it means that we want to switch all kinds of age, right, in this hypothesis class, capitalized age. So we want to iterate, go through all the small age here and find the best small age that makes the loss as minimized as possible. Minimized means as small as possible, right? And for the age that minimize the loss here, we 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 assign it to here. So argmin. So if you don't add argmin here, then the formula here means the loss, right? But if you add an argmin here, you are saying that I don't care about the loss. I only care about which age makes the loss small, and the expression, the value of this expression is the age, right? It's quite you see, it's quite subtle. So normally, if you don't write this stuff, you say something equals to LH, you are referring to the value of LH, right? But if you add argmin here, you are referring to the value of H instead of LH. This is quite subtle, right? In an expression, you don't even refer to the formula here. You are referring to the value of the H in the like subscript here, right? So it's very really subtle. So it means that I want to choose an age to make this as mean as possible, and the value of the whole expression is the age I choose. It's the age that minimizes the loss. Yeah. So now you can understand this, and that's expected, right? So the whole point of machine learning is that we make some larger assumption, which is the hypothesis class large H here, and we want to choose a loss function, a hypothesis function small h here that minimize the loss. Yeah, so that's all parts of machine learning. Right, a big part of machine learning is focused on this question. Now, how do we find the age, like efficiently? If you find an age with a low loss on your data, how do you know whether it will get examples right that are not in D? Oh, this is a good example. See, so say in this example, we found an age and say we are satisfied with this loss. This loss is 3 over 5. Suppose we satisfy with it. And of course, we are not satisfied, right? Because we want to get a even like lower loss, like an industry standard here. But suppose we are satisfied with 3 over 5, right? How do we verify that this loss is really good enough? So since we are like trained on this training data set, this is large D here, is training data set. We really want to apply this age on some testing data set, on some new data, and recalculate the loss again on the test data. Right? On the test data, we have a bunch of phi, have a bunch of age, have a bunch of x, have a bunch of phi, and we can still calculate hx and y and here and calculate the loss. So it's like on new data sets. So we already satisfied with loss on this history data set, and we get a new data set and we want to verify our model, and we say, oh, the loss is quite large on the like a new data set or on the test data set. It means that we are not doing a great job. Our loss is only great on our thin data, or it's only good on our training data, meaning that we are overfitting. So our age here, right, our prediction function, our hypothesis function here is overfitting on our training data. Means it works too well on our training data. It is like a sort of like just memorizing the question and answer of all the given stuff, and it's not trying to infer about the relation, right? say I give you a question and an answer, a question and an answer. You just memorize the match between question and answer, and you say, oh, I know the answer for question one is answer one. I know the answer for question two is answer two. You're not doing the inferring between why I give this answer, right? You're just memorizing the stuff. If I give you a new question, of course you won't be able to do that, right? Because you don't infer how I solve the questions, how I get the answer based on the question, right? You don't infer this. You just memorize the answer. Then you will get a perfect score on the training set. But on a new data set, you perform really poor. So that's what we call it have a low loss on our training data set B, but it get a really like awful results on the test data set. And so I will leave train test split as like a optional reading for you. So since I already sent this to you, so I won't send again, and you can find it already in the group. So train test split is really splitting a whole data set into a train data. Train data is D, and a test data, which means a new data set. And you find the hypothesis functions on the train data, which minimize the loss on train data. And you need to test this hypothesis functions on the test data to see if you still get a really or like a quite low loss on the test data. If you get a good result on test data, it means that you find a quite good hypothesis function. And if your hypothesis functions only work on train data, but get a really large loss on test data, it means that your machine learning model doesn't work. It just memorizes your answer instead of trying to learn, trying to dig the pattern, dig the relation in the data. Okay, that's the end of this lectures. Yeah, thank you.